Okay, this is an addition to the rate law problems that we've been talking about in class. And what we're taking a look at, and the reason why we're throwing this at you again, is this is a unique situation that sometimes comes up with rate law problems. And we want to know how to deal with this. And so let's take a look at this experiment first off and see what might be different about the type of problems that we've already dealt with in class. For one thing, we have our balanced equation. Everything's the same. We have three experiments. We're looking at chlorine dioxide here as one of our reactants. We're looking at fluorine here as one of our reactants. And we have the initial rate of reaction of ClO2F being formed. So everything so far looks pretty much the same. One thing that we probably do want to make sure we do, if we have moles per liters negative first, we're just going to call that molarity. Let's just call that molarity, makes life so much easier. And then over here on our initial rate of reaction or formation of ClO2, we have moles per liters negative first, seconds negative first. Again, let's just call this molarity per second and just make life a lot easier for ourselves. No big deal. Okay, so that's not really the big issue that I was going to talk about here. What I'm going to talk about with respect to an issue is let's look at our fluorine here, diatomic fluorine, and what we see here is we have a 0.1 for experiment 1, a 0.4 for experiment 2, and a 0.2 for experiment 3. Now my issue becomes that we do not hold any of those constant, and so we have to do a little workaround to determine our order of each of our reactants. What we do see though is we see that the ClO2 is being held constant in experiment 1 and 2. So let's go ahead and use those two values to determine our F2 concentration, or excuse me, our F2 order, which is relatively easy. So what we're going to do is kind of the same way we go about it is we're going to take our rate. So let's take experiment 2 over experiment 1. So let's take our rate from experiment 2, which is 9.6 times 10 to the negative third, divided by our rate from experiment 1, 2.4 times 10 to the negative third, is equal to our rate law constant, which we're going to cancel out from experiment 2 and 1. No big deal. We're going to go ahead and plug in our 0.010 molar for the ClO2, 0.010 molar for the ClO, 2 for the other experiments, so obviously those are going to cancel out as well. And then we're going to go ahead and plug in our 0.40 from experiment 2, and this is for our F2 here. And then we're going to plug in our 0.10, and of course these are going to be raised to our m power. Essentially, that's how we're going to determine our order for F2. And so let's go ahead and divide these out, and so we get 9.6 divided by 2.4 times 10 to the negative third equals 0.4 over 0.1 is also 4 raised to m. And so obviously m is going to equal 1. So that lets us know that within our rate law, diatomic fluorine is going to be raised to the first power. There's our first order. Now, as we said, we have kind of a little issue here going on because with respect to the F2, nothing was held constant. We had 0.1, 0.4, and 0.2, nothing held constant. And that's occasionally happens on these type of things, but we can deal with it. And here's what we're going to do. I'm going to go through and I'm going to pick again a couple experiments. Probably best because we're trying to determine what order ClO2 is, and so I'm not going to pick the two experiments where it's being held constant. Let's go ahead and vary those. So let's go ahead and I'm going to pick experiment 1 and experiment 3 to just try to see what's going on here. But we're also going to include in our values for F2 now that we know that F2 is first order. And so let's go ahead and do that. And so we're going to pick experiment 3 over experiment 1, but we're going to include more information. So again, we're going to do our rate law, and we'll put our rate first. And so our rate for experiment 3 over experiment 1, our rate is going to be 9.6 times 10 to the negative third divided by 2.4 times 10 to the negative third for experiment 1 is equal to the rate law constant over the rate law constant, which are going to cancel. then we're going to go ahead and plug our values in here now. So for the ClO2, we have 0.020 divided by 0.010. Now, that is what we're trying to determine. We're trying to determine what that's being raised to, but we actually have to include in the F2 here. The reason we included in, once again, is F2 was not being held constant here or here. So let's go ahead and include it in. So we're going to multiply this by 0.20 divided by 0.10. Now we've already determined from our previous example right up here that this is going to be first order. And so let's just keep it first order, no big deal. If it was second order, we'd have to actually put that in there. And so given this idea, let's go ahead and calculate. Let me just move this guy down real quickly here. Let's go ahead and calculate and solve for n. So when we go ahead and divide out our rates, 9.6 times 10 to the negative third by 2.4 times 10 to the negative third, we're going to get 4 again. We're going to go ahead and divide our 0.020 by 0.010. We obviously are going to get 2 raised to the n power multiplied by 2 raised to the first power, right there, raised to the first power, and there we go. And so now all we're going to do is we're going to go ahead and solve it for n. So before we solve for n, we're obviously going to, let's go ahead and algebraically manipulate this equation. So we're going to say 4 divided by 2 is equal to 2 raised to n. 4 divided by 2 is going to equal 2 multiplied by, 2 equals 2 raised to n. So obviously n is equal to 1. And that's how we go through and solve that, just by plugging that value back in. Okay, so let's go ahead and write our rate law now. So now when we write our rate law, we can write our rate law as rate is equal to our rate law constant multiplied by ClO2, which we just determined, having first order, and the F2, which we previously determined as being first order as well. So this would be a second order overall reaction, or first order with respect to either one of the reactants. Okay, then we can go ahead and calculate our rate law constant K with appropriate units. So I'm going to take my rate law that I just wrote, and I'm going to solve it for K. K is equal to rate divided by ClO2 multiplied by F2 concentration. And I'm going to go ahead and pick my first experiment, doesn't matter which experiment I pick, to plug in. And so I'm going to have to kind of jump back up here and look at my rate from my first experiment. Okay, so it's 2.4 times 10 to the negative third. Go ahead and scroll back down. 2.4 times 10 to the negative third. I'm going to double check my units on that. Molarity per second. Okay, just want to make sure it was not molarity per minute or hour. So we have molarity per second. We're going to head and divide that by the ClO2 concentration multiplied by the F2 concentration, both raised to the first power. And so we have 0.01 and 0.1. So 0.01 multiplied by 0.1. These are both molar, both raised to the first power, so we don't have to square or cube or anything like that. So let's go ahead and run this through our calculator here real quickly and see what comes of it. Okay, so we punched that in, and I've got an answer now of 2.4. Okay, let's look at our units here real quickly here. So our units, we have molarity as the numerator and molarity as the denominator canceling. That's all we've got to cancel. So we have seconds, negative first, and then we have molarity, negative first listed as well. And so that is going to be the value for our rate law constant for this overall second order reaction, first order with respect to both of the reactants. Okay. Then the last question says, calculate the rate of disappearance of F2 in experiment 1. So let's go back up there and take a look at what we have with respect. I'm going to erase some of these things off of my data table just so I can get a nice clean look at things here. And so the question asked for the rate of disappearance of F2. What we're given is we're given the rate of appearance of the ClO2F. So this guy in experiment 1, ClO2F, is appearing at 2.4 times 10 to the negative third molar per second. Okay, so that's it. That's the rate of appearance. So we're going to look at for the rate of disappearance of F2. So we're just going to use the stoichiometry to calculate this. So let's go back down here and say this. And so we have 2.4 times 10 to the negative, oh, I forget what it was now. I think it's negative third. Let me jump back up real quick and find out. Yeah, it's to the negative third right there, 2.4 times 10 to the negative third. And that was in molarity per second. And that is for ClO2F. And then we're going to use stoichiometry from the balance equation ClO2F with respect to F2. And if I remember right, F2 was a coefficient of 2, ClO2 was a coefficient of 1. Those are in moles, but remember molarity is moles per liter. So we can just assume moles is okay. Moles and moles. And so it's essentially, and I'm going to double check this because I'm going off of memory and make sure my coefficients are all correct. Oh, I had them backwards. So F2 is, oops, sorry about that. F2 is does have a coefficient of 1, not of 2. So I did get those backwards. I'm glad I double checked it. Erase that off there and there. And so this is a 1 to 2 ratio. So it's going to be half the rate. Okay. So the rate of disappearance of disappearance of F2 is going to be, we're just going to go ahead and solve this. And so we're going to get 1.2 times 10 to the negative third molarity per second, or moles, liters negative first, second, second first. There's our answer. Okay, so again, that's how we deal with kinetics problems where in the data that we collect, we don't have anybody held constant in one of the experiments. 0.1, 0.4, and 0.2, nobody has held constant. So we just plug those into the rate law equation once we know the order from our other reactants. Okay, hope that helps. Have a great day.